So, in the last lecture I could not complete the method of variation of parameters. So, let me quickly recall what I have done in the last few minutes of the lecture, previous lecture, and then let me complete it. So, what we are doing is that method of variation of parameters, method of variation of parameters. So, what are the things we have given? We have given two solutions y 1 and y 2, which are solutions to homogeneous equations. Therefore, L y 1 is equal to 0, L y 2 equal to 0, and then our idea is to look for a solution y of the form C t y 1 plus C 1 t y 1 plus C 2 t y 2, so that y is a solution to the non-homogeneous equation. So, y satisfy L y equal to R. What we have requested you to do a computation, and after doing the computation we have imposed a condition, because we have to determine C 1 and C 2 as functions of t. So, we require two conditions. Looking at the differential computation of L y, first to do the computation of L y by computing y prime, y double prime and substituting in L y, and which should be equal to L of y equal to R. We have seen a term. So, we imposed a condition C 1 prime y 1 plus C 2 prime y 2 is equal to 0. Once you impose this condition, then L y equal to R will reduce to the condition C 1 prime y 1 prime plus C 2 prime y 2 prime equal to R t. So, you see, so we have two equations in two unknowns. Here C 1 prime and C 2 prime are the unknowns, y 1 y 2 y 1 prime and y 2 prime are given to you to determine, so that therefore, there exists unique C 1 prime C 2 prime if the corresponding determinant of this matrix y 1 y 2 y 1 prime y 2 prime is not equal to 0. But what is this? This determinant is nothing but the Wronskian of y 1 y 1 y 2, and this is non-zero since y 1 y 2 independent solutions, y 1 y 2 is independent. So, we are through in the sense that this is non-zero. So, there exists unique y 1 and y 2. How do you, in fact you can write down the solutions quickly, in fact you can solve it, you can find it is a linear system with two unknowns. So, let me write down your C 1 prime. So, you will get your C 1 prime is equal to, let me just do it, but do the computation. You will get R y 2 by W y 1 y 2 and C 2 prime. If there are any mistakes, do the computation and we will see there are any mistake, R y 1 by, I think the computation is correct, but you can compute it and check for any errors. And so, you get C 1 prime, you get C 2 prime, integrate to get C 1 and C 2, integrate to get C 1 and C 2. So, this is a reasonably a very general method, and what it shows that to determine a solution to your homogeneous system, again we need to know two independent solutions. But when the equation with constant coefficients with a certain right hand side, we can write down the equation in a neat way. This is another method, the method of undetermined coefficients. We introduced that also, method of undetermined coefficient, undetermined coefficients. This is for some special class, because we want to complete the non homogeneous term with constant coefficient. when it is a homogeneous equation with constant coefficient, we already know how to write down the equations completely depending on the roots of the characteristic equation. So, consider one special cases, two special cases. So, you will take Ly is equal to is with a constant coefficient, but certain calculations is also true without the constant coefficient, but for the simplicity we will assume PQ are constants, PQ constants. Some of the parts will work even with that, but you can write with A, B, C, but A is non-zero which can be divided, you can write it in this form. So, we are interested in this is the Ly definition. So, a special right hand side Ly equal to e power a t form. So, we are interested in solving, want to solve, yeah, this is why we want to solve this. This is the equation we want to solve, L of y is equal to e power. Again this suggests by the same arguments which I have given in the class, here there is a y here which is missing. See y prime are all proportional, if y prime is proportional to y, then y double prime is also proportional to y, and that is why he proposed a solution of the form e power RT. But here on the right hand side e power AT is available. So, we want to get cancelled, the best way, one of the best motivation to look for a solution of that form. So, look for a solution of the form y is equal to some constant we do not know, a e power a t. So, if you compute y prime, so you will have y prime is equal to a e power a t, y double prime is equal to a square e power a t. So, if you substitute there, e power a t will cancel, this will give you immediately a square plus p here, p is constant, a p a plus q a q into equal to e power a t, that right hand e power a t, that will get 1. So, that is a into a square plus p a plus q is equal to 1. So, our idea is to find an a, so that y equal to a e power a t equal to 0. So, we need a to be divided. So, this implies a you can take it to be 1 over a square plus p a plus q, and this is possible if that is non-zero. So, that puts a condition, if you want to find a solution that immediately not equal to 0. So, this immediately suggests that we have a solution of this form if a is not a root of this equation. This is a thing which we have actually done, which we will see again is a kind of resonance type same. So, if you have a right hand side e power a t, then such an e power a t should not be. So, if you are proposing a solution to this equation of the form e power a t to the non-homogeneous equation, only that e power a t should not be a solution to the homogeneous equation, that is the minimum thing it is telling. So, exactly telling that e power a t should not be a solution to the homogeneous equation is the condition that a square plus p a plus q is not equal to 0. So, you have so that gives a solution. So, y t equal to e power a t by a square plus p a plus q is a solution, is a particular solution, is a particular solution, particular solution. We are looking for particular solutions if a square plus p a plus q not equal to 0. So, again, so what happens if a square plus p a plus q equal to 0, then look for a solution. Now you have an idea, then look for a solution of the form some constant a into t e power a t. So, you are looking for it, you know that why it is a solution, some c t into e power a t form, and that is t form. So, now proceed it. So, you are looking for the solution of the form, this is y, our y, looking for it. So, compute again, do a simple computation, you compute y prime, in this case y double prime, then that will imply, do the computation, I will skip the computation, what you will get is that a into 2a plus p equal to 1, you will arrive at this formula. So, that will give you a is equal to 1 over 2a plus p. Of course, then in that case 2a plus p should be non-zero if 2a plus p non-zero. So, you see first you got a solution, therefore, a 1 by 2a plus p into t e power a t is a particular solution in this particular case, okay, particular solution. If this has to be 0, it is in that, with that condition you are getting it p a equal to 0, q equal to 0, and you also need this condition, but you need a non-zero condition in that case. So, now what happens if both are 0? So, one more case left out. Suppose, so let us go this, suppose these two happens, that is a square plus p a plus q is equal to 0, 2a plus p not equal to 0, that is also equal to 0. So, what will happen? What is this situation first of all? This is the more interesting. You see 2a plus p is nothing but the derivative of this with respect to a. That means it is nothing but a is a double root. A is a double root. That is the situation. So, here when a is a root, that means the input function, the in the engineering terminology, such a kind of right hand sides are always called input function or a forcing function. So, if e power a t, if the forcing function has this e of the form e power a t, then a is not a root of the auxiliary equation, then you have an immediate solution of that form. On the other hand, if a is a root of this auxiliary equation or a characteristic equation, but if a is not a double root, if a is not a double root, if a is not a double root, then you have again solution of this form is a y equal to e power a t, a particular solution of this equation. If a is a double root, that means these two conditions are trying. So, try for a solution of the form, next level, try for a solution of the form y t is equal to a t square e power a t. All this will be independent, and then you can see, do the computation again, a simple computation you can do, and you can see that a is nothing but half. So, a complete independent solution can be obtained, therefore, you can get your particular solution of this case y particular of t is equal to e power a t by a square plus p a plus q if a square plus p a plus q not equal to 0. You will have this solution e power a t t e power a t by 2a plus p if a square plus p a plus q is equal to 0, but 2a plus p not equal to 0, and you have the situation half of t square e power a t if both are 0. So, it completes the complete analysis you have. So, you have your particular solution, you also know how to compute your complementary functions, what are called the solutions to your homogeneous system. The same procedure can be adopted. So, I will leave it for you as an exercise to leave it if you want to compute of the form equation of the form other types of signals, input functions or forcing functions are available. Say for example, suppose you have sin omega t or cos omega t, okay, one of them you can do that and you can actually determine the solution of the form. So, what you look for is that a solution, first you determine a solution of this form. If omega is not a root, again that kind of same homogeneous system, if it is not a solution you can proceed with the same form, and you can, if that is not a solution, next time you try omega sin omega t. So, the exercise is to find the particular solution, find a particular solution. So, this completely analyzes the situation when your solution when you have a equation, second order equation with constant coefficients, even with particular signals on the right hand side, you see, like e power omega t, sin omega t and other kinds of things which you can do it completely. So, what I will do is that I will in this particular lecture I would like to recall once again which we have done it in the first module, namely the spring mass system, because now you know we have already studied the spring mass system, but now you know how to write down the solution. I will not give the details here, but to complete a thing, and I want you to understand these equations is in the better way, you recall your spring mass system. So, this is a quick recovery, spring mass dashboard system, because now we will understand exactly what we want to do that one. So, for more details you go back to that problem. So, what is a spring mass system? My double prime plus cy prime plus k is equal to some external force F, and we have analyzed this in various situations. What is M? M is the mass, this is C is the damping, and K is the spring constant. What I would like the students to do when they read this thing, try to understand this equation, even in the case of exercises, understand in the case of RLC, circuit. Because it is the same equation which we have studied completely, but now since we know the solutions we can write it here. So, we have analyzed various cases. So, let me quickly recall all the cases. What is the first case we have studied? When C equal to 0, F equal to 0. This is called no damping and no free oscillations, is the case of free undamped system, free undamped, there is no damping system, the system moves, either it is at rest or if you have the system starts moving, it keeps on moving, the phenomena of Newton's law. So, in that case what we have done is that C is equal to 0, C is equal to 0, F is equal to 0, you can divide by M. So, you will have y prime square is equal to omega naught square into, there is a y here, omega naught square y equal to 0. What is omega naught? Omega naught is called the square root of k over m. This is called the natural frequency of the system. This is what we have done it. And this immediately, if you write down the auxiliary equation, now you see the auxiliary equation will be m square, I used r square plus omega naught square, which has complex roots, you see omega naught. So, you get complex roots and your solution will be a cos omega naught t plus b sin omega naught t. So, an exercise which probably at that time I have not given, which I do not remember, probably it given, write it in the form. This is better way to understand the system. Write it in the form, try to do this form y is equal to yt is equal to r cos omega naught t minus delta. So, you have these equations where r is equal to square root of a square plus b square and delta is equal to tan inverse of minus b by. Note that omega naught is given by k by m. So, it is not a constant. The constants are, so for a mathematician this is a general solution because it consists of two arbitrary constants r and delta. Here the arbitrary constants are given by a and delta. So, this if you look at it, r gives you the amplitude, cosine varies from between minus 1 and 1. So, this will vary between, it will be oscillates fully between r and r with a phase difference delta. So, if you plot this curve, you will get the solution, it will be plotting, there will be a phase difference. So, this will be your minus r, this will be your r with a phase difference. So, it will oscillate and the oscillation never stops as expected. The case 2 which we have considered in this, that is the first case. So, there is no damping. So, there is no external force thing. So, now we are taking the case C not equal to 0. So, you have provided some damping to the system like you are spring and putting it in an oil or something like that. So, you are providing a damping, and damping is understanding damping in the case of mechanical system as well as in the electrical system, which is nothing but the resistance there is important. So, you have F equal to 0, this is damped free oscillations, damped but free oscillations. So, you see in this case it is a homogeneous equation, and homogeneous equation you know how to write down here because m, c, k are non negative. In fact, m and c, in this case we are assuming m is always positive, we are assuming c positive in this case. So, everything is of course, k is also positive. So, you are assuming everything is positive in this case. So, in this case you can write down your solution which we have already obtained depending on the root of that. So, you will have a general solution of the form e power r1 t plus b e power r2 t. When is that? The roots are distinctive. If I write down that one, it will be c square minus 4 m k positive, and it will be a plus b t into e power r t if c square minus 4 m k equal to 0, and it will be e power minus c t by m 2 m maybe a cos some mu t can be exactly write down plus b sin mu t if c square minus 4 m k negative, and where what is mu? Mu is nothing but 1 by 2 m square root of 4 m k minus. This is what in the last class we have seen it already. You see, you can write down, and where r1 is in this case, what is in this case? So, in this case r1 r2 given by minus c plus or minus square root of c square minus 4 m k by 2 m. Here your r, the root should be minus c by 2 m, you see, and look at it, some interesting observation. C square minus 4 m k is the positive case. In that case it is a positive quantity, whether you put a minus sign or plus sign, it will in absolute value it will be thing. So, in this case both R1 and R2 are negative. This we explained, but let me repeat it because now it will be clear. It is negative, since R1 and R2 are negative, this will go to 0, this will go to 0 exponentially. The second case here, this term will go to 0, but then there is a t term, but then t into e power r t, where does it will go? The exercise is that this will also go to 0. So, here is a simple exercise. Most of you will have a tendency to say that exponential goes faster than polynomial, which is a fact, but what is the meaning of exponential goes thing? So, you have to prove this. Just mere words of telling that exponential goes faster than polynomial is not enough. You have to show that t e power r t goes to 0 as t tends to infinity, where r is a negative quantity. So, you prove this, otherwise that is not true. So, proving this fact is the meaning of that exponential goes faster than the polynomial. Now, here the third cases. So, there are in the first two cases, this case and this case, there are no oscillations and this term goes faster, that means this has to be m and k are fixed quantities. All this sign changes because of c, and c is the one which we are controlling in the damping. So, when you want to make c square minus 4 m k positive, it means that you have to add more damping to the system, and if you reduce that damping you will reach a situation here. But even if you reduce the damping, it still goes to 0, this term is still goes to 0, but slightly slower way, but still exponentially. But if you reduce the damping still further, you will reach a situation here, but some damping is required, but because if c is positive, still there is a negative quantity sitting here, you see, c is positive. So, this is minus of that. So, still negative quantity sitting here. So, this exponential term is still there, but the difference when your damping is reduced further and further, you will have a term of this form which will have an oscillation. This will behave like an oscillation, it will have an oscillations behaving, but then this will kill. So, the oscillations will kill thing, and we can write that third case, third situation, you can write it as third situation. You can still write the third situation as y t is equal to r e power minus c t by 2 m. Same way, do it as an exercise, cos of mu t minus delta, you see. So, this is your now amplitude, the amplitude decreases, oscillates, is when there is c equal to 0, this term is not there. So, its oscillations are not reducing, but since c is positive, the oscillations are still there, but its amplitudes reduces. So, if you plot this graph here, you can plot two curves here, what the curve is also you can plot it. This curve is nothing but minus r e power c t by 2 m. This curve is nothing but r e power minus c t by 2 m. This is at the point minus r, this is at r, and this starts oscillating, it touches, see, oscillates like that, it decays like that, it goes to 0. So, that is a situation when there is a damping. Now, the final situations which let me not do it completely, but let me do the next case. Suppose c not equal to 0, and f not equal to 0, but I do not want to take arbitrary for f, it is an input function, but so let me try with f naught is equal to cos omega naught t with f naught not equal to 0. So, you have an external frequency coming here now, but then there is a damping is provided. So, this is called forced damped vibrations, forced damped vibrations. You see forced damp. So, what you can do is that, so it is a case of non-homogeneous situation, and non-homogeneous situation with C not equal to 0, you know for the homogeneous part you know how to write your homogeneous solution, which I already described in the just previous part, and plus you can write down a solution, particular solution you can write down, because it is of the form cos omega t you can do. And what we have observed is that as t tends to infinity this goes to 0. So, as t tends to infinity what will have, the y will behave like y particular solution, you see. So, because y homogeneous part, this part goes to 0 as t tends to infinity. So, the behavior of your solution will behave like y, and this is not thing, it is according to that you can exactly write down your equation, write down your solution. So, what I suggest you to now solve this equation, because it is a cos omega t, using method of undetermined coefficient you can find your y particular solution. This y home we already determined. So, you determine y particular to find the solutions and see that there will be oscillations and decay everything according to that situation. The one interesting case is that we already seen that when there is no damping, and no external force acting on it, there itself you have vibrations which is not decaying. Now, we will have the most probably either unwanted or desirable according to the situation. In mechanical system it is undesirable, because if there is no damping, at the same time an external force coming and acting on the system. So, you will have a situation where C is equal to 0 and F is equal to f naught cos omega t or sin omega t with f naught not equal to 0. When C equal to 0 you have your solutions, and this gives, this again reduces to two cases, because when you have a omega t here, when C equal to 0 there is a natural frequency omega naught. So, if you looking for, this is a natural frequency, if you just the previous introduction, when you have a solution here cos omega t, and if this omega happen to be the solution of this here in the homogeneous equation, then the solution will be differ. So, if omega, the case 1 in two cases, the natural frequency omega naught is different from omega, then there is no problem. You can write down the solution and nothing interesting. Then what we have seen, nothing interesting, nothing new, let me write it. You will write down the solution, you will have some oscillation. So, if you have, even if there is no damping, it will be, you have a homogeneous system which is oscillating, which we already seen that, a homogeneous solution, then you will have a component of a particular solution and there is absolutely no problem. The second case, when you have an equation omega is equal to omega naught, but then cos omega t cannot be a multiple cos omega t sin omega t cannot be the solution of your homogeneous system. So, the solution in this case will look like little more interesting. You will have a solution due to the homogeneous part cos omega naught t plus c sin omega naught t, and then the particular solution will have another factor. The particular solution will be of the form, let me write down f naught by 2m, this is okay, this is a small constant, What the fact is that you have to try a solution. If omega is a solution to that homogeneous, cos omega t is a solution to your homogeneous system, you have to look for a particular solution of the form t cos omega t or t sin omega t, and that is what it gives you. You will have a sin omega naught t. Now look at this fact, this will oscillate without reducing your vibration amplitude, but here you see a factor. This is not only oscillating, as t increases, this amplitude of this factor, the amplitude of this portion increases. So, if you have plot your graph this one, you will have something, initially there may be some vibration, as t increases the vibration is. This is what is called the undesirable oscillation, and I explained in my first module unwanted vibrations in the case of mechanical systems and the Tacoma bridge collapse, etc., which we have discussed. On the other hand, the same system, when you are trying for an RLC circuit, even if a small current comes and this equation represents the second order linear equation with constant coefficient, represents the equation for I. And then what it happens is that if you have an external frequency coming which coincides with your natural frequency, that gets its amplitude gets becomes larger and larger, and you can get the signal, and that is exactly what you do by in the tuning. So, many examples in this situation can be done, worked out. So, just solving equations using the methods or theory is not enough, one need to interpret the solutions according to the problem, type of problem one is studying. This more or less completes which I want to tell in this module, but before completing this particular module on second and order linear equations, I want to introduce one of the important concept, not only for this initial value problem, it will also come in boundary value problem, and this is also appears extensively in partial differential equations, which this is called the a concept of Green's function. So, I am not going to do it too much of Green's function here. My idea is just to motivate you why Green's function, the Green's function comes naturally in this setup. So, Green's function basically used to represent solutions, to get representation formula. But why do we expect such a Green's function, and what is a Green's function in the setup of these second order equations? So, let me recall your operator once more, maybe a little later I will call it. So, let us start with the differential operator d by dx. So, this is a differential operator which we are studying now, you are comfortable with that one, and you have the finding derivative is a forward problem. So, you already seen that forward problem. That means you have your du dy equal to f, given f, given u, find du can be computed, that is a forward problem, no doubt in that one. So, you have a so you can think that d by dx is a mapping probably. As I said, it is a more motivation, one can make it precise defined. So, you can think it as a, for example, you can say that it is a functions from C1 of some interval t naught to t to going to C of t naught to t, you see. So, you take a differentiable, continuously differentiable function, differentiate. So, if you take u here, your du by dx equal to f belongs to here, you see. On the other hand, if you do this is the differential calculus. On the other hand, when you go to an integral calculus, you are trying to invert it. We are trying to, loosely speaking, loosely, we are trying to, we are inverting d by dx, the operator d by dx. That is what you are doing it. So, these are different interpretations. We are trying to invert means given f, find u, that is what you are trying to do it, find u, so that du by dx is equal to f, you see. And that is what we eventually calculated, you have calculated ut in terms of I have used t, since I am throughout using t, let me use t only. So, let me use d by dt, d by dt, d by dt. So, you have d by dt, you have du by dt, and this is formally represented by f of t dt. You see, it is a formal representation. So, you have in some sense d going to an inversion of integral. So, in other sense, if you have your fundamental theorem essentially tells you that integral of d, you are trying to get some identity, you see. That is what you are basically trying to do, that one, an integral calculus problem. So, thing is that whether we can do some representations. So, you are trying to represent your solutions u is of this form. So, now you have a general operator L, I have a general operator L, I can think that L is an operator say from t to C2 to T naught to T, going to say C of T naught to T, where L of u. So, you are y here taking going to L of y, by definition what is L of y is equal to y double prime, p q are given to you, p and q are given to you, y prime plus q t y. This belongs to C naught T naught to T. So, you have an operator L mapping from the thing here. So, what is the meaning of solving it? So, what is the ODE now we are trying to do it so far? ODE given R continuous, given R, solve for y, right, solve for y, satisfying Ly. So, this is the forward problem basically, given thing is forward, that is not a problem. So, ODE solving is that you are trying to, in the integral calculus set up in a more general ODE, you are trying to invert your ODE, you are trying to solve for L of y is equal to R. So, I can introduce a mapping. So, I can introduce a mapping S from C of T naught to T. You do not have to worry about the spaces right now, but that is not the issue here. T naught to T, where given R, you are finding the solution y, which is nothing but SR. I call this is equal to SR. So, if you put initial condition, you know that there is a solution given as put the, so in particular if you put conditions y 0 is equal to 0, y prime of 0 equal to 0, this S will be linear. If you put other conditions, you will not get linearity, but that is okay. If you put that conditions, you have a basically linearity. You are trying to invert this kind of equations. So, our question is that analogous to this one, given you are getting a representation. So, looking for a representation. So, looking for a representation, looking for a representation of the form, you want to represent y as a function of t, that is nothing but SR as acting as a function of y. So, S is an operator, you want to get a representation of this operator S in an integral form. Can you have an integral form? G of T of psi d psi R d psi. So, can I get a representation in the integral form? So, it is a slightly more general, you cannot have an easy way integral form, integral representation. In particular, not in particular, sorry, if you realize that one of the classical theory is finding solutions to integral operator where there is a certain kernel is given. So, given a kernel, this we can call it a kernel. In general, we call it here a Green's function. So, when you are given a 2 variable function and you can introduce the integral operators which are linear integral operators, in fact the development of linear theory actually began from the integral operators theory. So, integral operator. So, you are looking for such a function is possible. So, you have a, is it possible to find a 2 variable function g which is a function of t and psi defined for where t psi greater than or equal to say t naught, and can we find such a g so that you have a solution representation for the, and that g should be independent of course the forcing term. So, let us see, let us try to compute formally which also can be justified. Suppose assume such a g exists. How the assume such a g exists? Do not worry about the computational aspects of it, which one can justify and prove the precise result. As I said, the motivation of Green's function is more important, we are not going to spend time. So, you compute your y prime t. When you compute your y prime of t, so this we will define say probably from t naught to make it precise t, and you should know how to take the derivative. This is a simple formula which probably we may do it in the our preliminaries. When you do the computation, you can take your t naught to t. You now let me write this is with respect to t, you are differentiating with respect to t, t of psi r psi d psi, and then there will be a boundary term. How do you find the boundary term? You just put psi equal to t and differentiate. So, that is nothing but g t t r t, that is a boundary term. It is easy to calculate. You put the limits and differentiate the limits. That is a general formula when such a, you can integrate from alpha t to beta d, integral alpha t to beta t and 2 variable function how to take derivative. Now, compute your y double prime of t. When you compute your y double prime of t, so you have t naught to t, I will g t t of t psi r psi d psi plus you have already computed g t and put evaluation at t r t, that is coming, this is fixed. So, that will not come. Now, here there is a difference, you should not be differentiating with respect to the first variable, you have to differentiate this as a, now when you are differentiating you have to treat this as a single variable function and you have to differentiate. So, there is a difference between when I write here dt of g t t r t. So, do not write g t at t t, that means when you write g t at t t means that you are differentiating only with respect to the first variable and substituting for psi equal to r t. Here it is not like that, you are substituting and then differentiate. So, you do a bit of calculations. So, you have calculated y prime of t, y double prime of t, substitute in the equation. So, you will have L of y, your L of y of t, L of y of t, you can actually do these justifications t, because assuming g, we are not introduced g yet. So, you will have L of g, the corresponding L of g, of course with respect to the first variable. The second variable xi is nothing but a integration parameter, but the differentiation and the differential operator is with respect to the first variable, not the other one, r psi d psi, plus you will have few terms here. For example, you will have g t t r t plus you will have a term p t into GTT RT plus you will have a d by dt of GTT RT. Okay. So, you have that kind of term, you can do that one. So, when you do this one, so this motivates us to define, we want this to be R. The best way to define R is that for each parameter you have to introduce the parameter properly. You define that to be 0 for each of that parameter appropriately. So, you have to introduce that parameter that gives you. You want to be RT. So, you want this as a to be 0 for every t. You want this GTT to be 1. You want this GT of this is equal to 1. So, that you get your RT, and this you demand 0. Once that demands 0, d by dt of that also will be 0. So, this first to introduce the Green's function, introduce the Green's function g t psi. I introduce this in a very nice clever way. One have to introduce. I introduce g t psi for psi greater than or equal to t. So, I will introduce g t psi for fix psi. Yeah. So, how to introduce, you fix psi as a parameter. So, I am introducing fix psi greater than or equal to t naught as a parameter. Okay, I want to treat it as a parameter. So, what I will do is that, so you have t naught here, I have some psi here. On this portion I will introduce the problem. So, I will introduce the problem L G, this is the differential operator is with respect to t parameter, and psi coming because I am introducing that the problem in for psi to t or whatever it is. So, you see, so I need conditions at psi. So, what are the conditions I will put at psi? I will put GT at psi equal to 0. I want G psi equal to 0, GT at psi is equal to 1. So, you see R is not coming into picture here. So, you introduce this problem. Now, this problem by uniqueness you have that solution, unique solution which is smooth enough. So, that everything can be justified whatever I have done. So, you have introducing this problem. On the left side you have to introduce for entire interval, you define g t psi equal to 0 because it is defined only for psi greater than t greater than or equal to psi. Okay, so, the problem is t is here. So, you want this one. So, g t psi is equal to 0 for t in t naught to psi. So, you can complete it. And so, you have a Green's function. So, you are defining on that interval, you are defining that one. Then you can actually prove now everything. So, you have your solution operator y. So, that will give you your solution operator y is equal to SR, that is equal to integral of. So, it is how this quite often this is introduced as an arbitrary way, but this is naturally we are demanding a representation g t psi SR acting at t, y acting at c, r psi d psi. So, you have a nice representation of this thing. Okay. And you can actually do little more using the variation of parameters etc. In fact, one can do a computation little more. Suppose y1 y2 be two independent solutions, two independent solutions of homogeneous system. Then you know, see look at here, even though it is a homogeneous system, you have a non-homogeneous parameter. So, even the solutions of this can be computed using the variation of parameters, using exactly what we have done to compute the non-homogeneous system. Even for this equation you can use the variation of parameters using the two independent solutions. Using the two independent, so these are all, I will leave it as a simple exercise. You can do that one. Y1 and Y2 is a homogeneous solution, then you can actually compute g of t psi to be nothing but y1 of psi, y2 of t, careful with psi and t, minus y1 of t and y2 of psi. So, you see, so you have a nice representation of that divided by, so you have to divide w of, you calculate the Wronskian of 2 and evaluated at psi, that is something you have to do that. So, you have a representation of solutions. So, if you write down now your solution, so if you are, so if you can write down for your solution with Ly equal to 0, y at 0 is equal, Ly is equal to r, with y at 0 is equal to, please note that the solution satisfies the homogeneous conditions. So, you will get y 0 is equal to 0, y prime of 0 is equal to 0. So, you can write down the solution your phi evaluated at t in a nice form. So, you are integrating only with respect to xi here. So, you can write down and you have an you are integrating with respect to xi. So, you can, this will come out, y2 will come out. So, you will have phi t into y2 of t minus y1 will come out, the remaining integral will be psi t into y1 of t. And what is your phi t? Phi t is nothing but L by t is equal to g t psi r psi. So, this factor you have to take it. So, is equal to integral t naught to t, you get y1 of psi r psi d psi by w evaluated at psi y1 y2, and your psi t will be integral of t naught to t evaluated at y2 of psi r psi, you have w of psi. So, you have a good representation of your thing. So, the Green's function, the main idea of this talk part is to introduce the Green's function. So, you can introduce this, and but what I say that this looks simple, but understanding the Green's function fundamental solutions are fundamental in the other situations. So, you can see that probably when we deal with the boundary value problems, we will come to the Green's function little more. But so, there is a beautiful representation using Green's function. With this we complete the this particular module on linear second order and linear first order equations. In another module we study the nth order linear equations and nth order linear system. There our main focus will be to understand the stability of equilibrium points. Hence, we will be using the linear algebra extensively. Thank you.